thrilled to welcome you all here in the room, and also folks who are listening in via the web to Syracuse COE's February Research and Technology Forum. So folks who have been with us before for our program know that every month we offer a topic of interest to our collaborators and our stakeholders relating to advances in research or technology. And this is a program that's it's brought to you by the partner program at Syracuse COE. If your firm and institution is not currently part of our partner program, we invite your inquiry and invite you to join us. To moderate our program, I'm pleased to introduce Andrew Maxwell, who's Senior Program Manager and Innovation Strategist at the CNS companies. CNS is a charter member of Syracuse COE, and Andy is so kind of well known in the Syracuse community, has joined them recently. He's had a distinguished career in public service, and he brings significant experience and expertise in government and public works projects. In his new role, Andy supports CNS's many government clients by integrating and coordinating CNS's diverse skills to deliver innovative and customized solutions. And his background with more than a decade in planning, community and economic development, public policy, and civic innovation gives him a specialized ability to create creative, operational, and programmatic solutions. Folks surely know Andy was with the city of Syracuse. He was the founding director of the Office of Innovation and its innovation team. Previously, he was director of the Syracuse Onondaga County Planning Agency, where he promoted sound planning and that fostered greater economic vitality, environmental stewardship, and improved quality of life. He's also the founding director of the City of Syracuse Bureau of Planning and Sustainability. He coordinated the completion of the Syracuse Creek Walk and the connective corridor. It's really very exciting for all of us to see Andy in his new role with a Syracuse COE partner. We look forward to many opportunities for collaboration, and we're very pleased that he's with us today to moderate today's Research and Technology Forum. So without further ado, I'll turn the floor and the microphone over to Andy Maxwell.
And, good afternoon, all, and thank you, Ed, for that kind introduction. It's been my pleasure to work with Ed and the team here at the Center of Excellence in years past in my previous roles, and I'm certainly excited to do so again in the future in my new work with the CNS companies. So our program today is I'm going to now introduce Dr. Doelle, who will give a presentation, and then we will follow that with some question and answers before we wrap up the program. Dr. Doelle, Dr. Klaus Doelle has over 26 years combined professional experience in the commercial sector, including chemical process development, paper manufacturing, materials, design, manufacturing, energy production, wastewater treatment, and patent management. He has over 11-year combined academic experience from Brandenburg University of Applied Sciences and Germany and the State University of New York College of Environmental Science and Forestry, Department of Paper and Bioprocess Engineering, and Division of Environmental Science. Dr. Doelle's research interests are focused in the area of pulp and paper and related environmental topics, including design of constructed wetlands, subsurface bioreactors, fossil energy, bioenergy, hydropower, water and wastewater treatment, paper recycling, paper development, filler materials, energy savings, renewable energy and processes, engineering, machine and process design. Results of his research efforts have been published in over 610 publications, including 140 papers, articles, invited papers, presentations, and discussion panels. We can add one to that today. In addition, Dr. Doelle's past research efforts have led to 66 granted patents, more than 250 filed patent inventions, and in addition, over 50 invention disclosures. Very impressive record, to say the least. Please join me in welcoming Dr. Klaus Doelle.
Thank you very much for this nice introduction, Andy. And yeah, thank you very much for having me here, and good evening. So I think we'll have a nice hour about topic, and I animated that. And thank you for the Syracuse COE for inviting me. And our topic, I was talking with Ed, and Ed, thank you very much for inviting me. And we were chatting around how we named that, because there's so much stuff in it. And we came basically up shaping a greener future for New York, what we want to do. And of course, we want to use the state canal system to do that. And we also have looked at the green belt, chemistry belt, and the Rhein-Main-Danube-Canal System. And actually, this part of the presentation is what I presented in September last year at the World Water Conference, Canal Conference in Syracuse. So the first part, and then I'll edit some other stuff to it, which is more relevant to the New York Canal System for the future. And please, since this might be a very long presentation, so I don't know how it goes, ask questions right away, so you don't have to write them down and memorize them or forget like I do. At the end of the presentation, I cannot remember it anymore. So just ask them right away. And you will see down there, I have basically ESF and the Trinity Institute. I also have the Hafen Straubing Sand, which is a harbor in Germany we'll talk about. And I also have the State of Bavaria flag there, because some of this information came from the State of Bavaria, and the Straubing called Renewable Energy Region, and then of course the COE. So I have the credits right away there. So okay, let's get started. So those are the topics for today. So brief introduction, then we'll talk about the Rhein-Main-Danube Canal System. We'll talk about the Danube River Port Straubing. Talk a little bit about Great Lakes shipping, because maybe not many people know about that, or kind of forgotten and still there. And then something about the Erie Canal System, or New York State Canal System. I had to put that in there a little bit about hydropower. So and New York State Canal biomass supply, but biomass study that has been done in 2013. Just a little brief update on that. Something about green industry that's possible, imagining the potential. So we're talking what could be used, and then kind of what does it take. So let's get started. So Rhein-Main-Danube water system. So of course, this is not the Danube water system. This is basically in Shanghai. And if you look at the Shanghai or the Chinese rivers, there's a lot of going on in the waterways. They are constantly, and that's day and night. So whenever you go there, there are ships going up and down, and they are transporting all kinds of goodies. And it doesn't matter if it's in Shanghai or wherever. The waterways in China are used heavily for transportation of goods. And then we know this. This is actually a picture from Germany. And if you drive in German highways during the week, that's basically what you get. One truck on another, because nowadays everything is just in time, and the warehouses are on the road, basically. Yeah. And another problem is in Germany it's different. Trucks are only allowed to drive 60 miles an hour, not faster or even slower, and cars go very fast. So that kind of creates a problem, and you cannot pass on the right side. You're only allowed to pass on the left side. So there's always, especially around the big cities, there's a big problem with congestion, and sometimes you get traffic jams. They are 10 miles long and things like that. So that's the daily situation. Okay. We want to avoid that. So we'll have to do something else, save energy and save fossil fuels and CO2 and things like that. So let's talk a little bit about the Rhein-Main-Danube waterway system. So actually the Rhein-Main-Danube water system is actually 3,500 kilometers long. So it basically stretches like it's there from Rotterdam with the Rhine going all the way down there. And then we have the Danube, which is actually going all the way down here into the Black Sea. But this was not connected. The river Rhine flows in the river Rhine, but this was not connected here. So the Rhein-Main-Danube-Canal System basically connects the Danube with the Main and the Rhine. So you can basically take a boat and go all the way down into the Black Sea. So the river Rhine basically, which is this here, it's the second longest river in Germany. It's about 760 miles long, yeah, and it has about a little bit over 100,000 cubic feet per second discharge. There are 19 main locks in the river and dams, and about 1,950 megawatts of hydropower installed. The river Main is actually the longest river in Germany, and it's a little bit smaller. It's 527 kilometers long, about 200 cubic meters per second discharge, so 100,000 cubic feet per second. There's 34 dams and locks, and about 127 megawatts of hydropower installed. So there's quite some big hydropower installed in those two rivers. If you look at the river Danube, that's the second longest river in Europe, and it's about almost 1,800 miles long. Yeah, and it has about a discharge close to 250,000 cubic. That's the average discharge over the year, of 250,000 cubic feet per second. Yeah, then 59 dams and locks, and at the first 1,000 kilometers there are 272,578 megawatts of hydropower installed. I have a slide on that later. And that's the whole capacity of the Danube watershed, which is pretty big. So this is basically the Rhein-Main-Danube, the Danube watershed here. Yeah, the Danube watershed reaches basically from Germany over Switzerland, Austria, Czechoslovakia, all the way down to the Black Sea. Yeah. And
what are the dots?
The dots are all hydropower plants. So the Danube basically is actually hard to see, but it goes all the way this way, and then you don't see that. Austria and Switzerland, there's a lot of hydropower plants because there's a mountainous region, so a lot of high evaluations, which makes it perfect for hydropower plants. A lot of storage hydropower plants with pump capacity, etc., etc. So the most is installed here, and then there are some larger power plants installed along the river Danube or on the rivers that basically feed into the Danube. Yeah. At some point, the Danube is pretty big. It's like comparable to the Mississippi.
I don't know, Brad.
Yeah, sure. No, just ask questions.
Are the hydro plants, is the infrastructure in there to move the power, or is it used locally where the hydro plants are?
Well, for the larger one, of course, there's infrastructure with high power lines, but for the smaller ones in the mountainous regions, they are designed for local power use. So, especially in Austria and in Switzerland, they are mainly local, and there's a lot, so because there are not that many coal-fired power plants, a lot of energy comes in these areas from hydropower. Does that answer the question? So, okay. The Rhein-Main-Danube-Canal System, again, the Rhein-Main-Danube-Canal System, this is just this little stretch here. Yeah, it's 170 kilometers, about 106 miles long, but the highest elevation is about 1,300 feet. So that's actually the highest waterway in Europe. So to do that, it dates very, very long back. The Rhein-Main-Danube-Canal System was actually developed early in the 1800s, dating back to Europe. And it was finished in started in 1962 and finished basically 30 years later. Because like if you do large street projects or something like that in Germany, permitting takes a very long time, and you have to fight all the environmental regulations and things like that. But anyway, it was finished in 1992, and it costed about $2.3 billion at the end. Yeah. And basically what it does, it connects Bavaria to the North Sea harbors, yeah, because that was not possible before, and to the Black Sea region. So, or the North Sea harbors also to the Black Sea regions, because there was no continuous shipping possible. Now it is that those ships going on, or barges, they are able now to go through the whole waterway all the way to the Black Sea, so you can transport goods back and forward. And it connects also Bavaria to 15 other European states. So that's a big thing too. There are 16 locks to overcome the 243 meters of height. They're lifting locks. The highest lifting lock is about 24.7 meter elevation. So that's then basically, I have not the number in there, but that's probably, it's pretty close to almost 80 feet in lift. And the locks have a maximum length of 590 meters, which is close to 600 feet. So could actually handle a barge that's 600 feet long, theoretically. It also pumps 125 million cubic meters of water to North Bavaria, because by moving the water up, you're also pumping it there. So it also has a purpose of supplying water from one side to the other side. So for agricultural purposes, things like that. So there are many different reasons to where basically there to generate this water system. And here a little bit a closer view. So this is basically the state of Bavaria. So that's the largest, one of the largest states in Germany, and the canal is basically here. So that's basically what it shows. So there's Würzburg, so some by Schweinfurt, so that was kind of Brandenburg, and then it goes from the Main in Brandenburg, it goes all the way down to Kelheim, where the Danube is. And then Straubing actually is not here. Straubing is basically somewhere in this area. Yeah. And this here actually, well, it's German here, but this is actually the continental water divide. And that was one of the problems to generate the system, because the continental water divide, from here, everything goes to the North Sea, and everything from here goes basically to the Black Sea. And here it shows kind of where, like if you look here, again, here, European water divide, and it shows basically kind of some of the older canals that were developed around 1834 to 1845. Very smaller canals, but shipping was not big at it, but you only had small barges like in the early when the Erie Canal was built. Yeah, but it never was connected totally. The river Rhine and the Danube never were connected totally to each other. So, and that's why the project was initiated in the 1960s. And this actually shows basically from the mine the individual logs, where the logs are and the lifting height. So you're going basically up and then you're going down. And as you can see, the Danube actually has a much higher elevation than the river Main. So from here, basically, you take water from the Danube and you basically move it basically this way. And then the continental water divide, you have to go all the way up to 400 feet, which is about 1,300 feet, and then it goes basically back down. Again, this shows the first part of the waterway. A little bit, and this actually gives the distances in between the individual logs. So it's not much. No, this is just about 4 miles, 5 miles. There's not much difference, not much distance between the individual logs because it's so short, and you have to climb up to such a height to move the ships up. and then on the other side it's a little bit easier. The distances are a little bit longer till you reach the Danube River. So now a little bit about the Danube River port Straubing. So this shows kind of the location of the Straubing Danube port. So Straubing is actually close to the Czech Republic in Austria, so it's just probably a half-hour drive on the Autobahn, depending on the speed. Then you're in Austria or you're in the Czech Republic. Yeah. And then, like I said, it connects all those states in Europe basically with Bavaria or the rest of Amsterdam, Netherlands. So basically, companies could ship now all their goods from the Danube River or even from the Black Sea all the way up to the big ports in Rotterdam, if necessary, because from the Black Sea it might be a little bit more difficult to ship your goods to some other places. That's kind of a little image from the Danube port Straubing. So you see those barges sitting there. So those barges are, they seem maybe small, but they're probably about 100 meters, 300 feet long. So they're quite some big ships. So they're actually a little bit too big to for the Erie Canal, because the canal is much smaller. But it seems to work. So Straubing is, for the state of Bavaria, the area that was devoted to clean energy. So there's also the University of Munich, the Carmen Institute, that all deal with the development of clean energy. So the whole city is basically focused on clean energy, and that's why they also have the harbor there. And then they have basically like pilot plant settings for production of ethanol from straw. So that's a big chemical company that installed a pilot plant there, and they're producing ethanol from straw in a pilot setting. There are big warehouses there. There are mechanical engineering companies there, and there's some bioenergy companies there. There's ArcelorMittal there, and all those companies, they move basically the goods back and forth. So like if you look at the Bavarian forest, for example, it's about 1.5 million tons of wood is annually produced that needs to be shipped somewhere to sawmills and things like that. So the river can be used for that. Bavaria produces in the area around Straubing about 1,300 million tons of sugar beets. So sugar industry is a very big industry in this area. It's seasonal, you know, sugar, potatoes, it's seasonal, but stuff needs to be shipped back and forth. Yeah. Or potato starch, grain, things like that. The area is probably about the size from Syracuse. There are about 140,000 inhabitants. Yeah. This bioenergy created about 4,000 jobs. Yeah. And that's about 11% of the total job market there. And as you can, oops, too fast. So the successful performance on the biomass, you can see on how the shipping developed and how biomass went up for shipping. Also, rail shipping increased because the port not only has a connection to the highway system, it has a connection to the waterways, and it also has a connection to the railways. So you can either decide what good you want to ship and how far you have to ship, because it always comes down to the economics. And for some goods, it might be maybe better to use the rail. You will see that later. So here are some of the. This is actually the port that was generated about 25 years ago, and you see this is ArcelorMittal here. There are some mills that produce dog food and all kind of other, and they get actually all their goodies with or products shipped with a boat. There's a large storage of storage places that have logistic centers, and we have clean energy companies there, etc., etc. And then this is planned here. There's a container terminal will be planned for the future, so it will have basically, we could ship containers here and then load the containers on rail and then ship the containers with the rail to the different locations in Germany or in Europe. That's not in place, that's planned for the future, because it makes sense to ship the containers with ship instead of with the rail or with the truck. So this slide gives kind of a how the green belt basically is envisioned. So since you cannot get it from everywhere, so there's a certain range where you can get your goods transported through the river system. And each area is a little bit specific. One area is more, they produce corn feedstock. The other area produces wood, and some areas produce straw. Because if you have a lot of wheat production, you also produce a lot of straw, and straw is not commonly used. It's a waste product. It's either plowed under, or you could make pellets out of it. But if you have, and I show that later, a straw bale or loose straw, if you load up a truck, there's not much weight on it. If you bale it, you can get a little bit more on it. If you make a pellet, you can get even more on it, and then it makes sense to ship it much longer distances. Because for straw, for example, you also could use it and make biogas out of it. So you can put it into a biogas plant and produce, make methane out of it and feed it in the grid, and or make electricity out of it. So, and wherever those locations are, so you can build now big plants and you can ship those raw materials much longer distances where it makes sense, instead of making small satellite locations for a small range of customers. So you can make a big one where you can supply a much bigger region, and I will talk about that a little bit later. So, and mainly used by shipping. So, and they call it basically green chemistry belt, because all the main oil products, they arrive in Rotterdam with the tankers, and then it's distributed to the companies that convert those fossil fuels into energy products, plastic products, etc., etc. And the new Waterway basically allows now also to use, because it only makes sense if you produce something on a larger scale, because then larger scale makes the end product cheaper. So companies can now ship basically their products and their raw materials from any location along the Danube all the way up to the Rhine, or these products also can be moved there. So vice versa, so it's a win-win for everybody on the Waterway. Yeah, and the Hafen Straubing is actually one of the largest harbors in Germany on the Danube, and in Austria there are some smaller harbors, but over time I think it will develop, and then there will be more shipping going back and forth. So that being said, so that's kind of what is already implemented. It works. Yeah, the harbor is there. The goods of shipping with barges is already proven. It's working. Trucks are replaced, railways replaced, or a combination of both, depending on the feedstock. It always depends on the economics. Okay. So, are there any questions so far? Okay, cool. And we'll go ahead. So now I want to talk a little bit about Great Lakes shipping. So, and this is actually, I got most of my information for that. So where do I get that from? So that is kind of accurate. So I use the Army Corps of Engineers. So that's the Army Corps of Engineers map. So Great Lakes, there are a lot of harbors actually around the Great Lakes. It was kind of good experience for me too, so I learned something while doing that. And I was not aware about all that. Since I lived a while in Wisconsin, I know the big locks up on the great on Lake Superior that connect Lake Superior basically with Lake Huron or Lake Michigan. So I know those locks, and it's quite some interesting to look at those. But it was really interesting to see how they do that, because the same would apply for the Erie Canal, because in the wintertime there's no shipping because it's frozen. So the Erie Canal freezes too in the wintertime. So we only can use it during the summertime and the fall time, and as soon as the weather is too cold, or cannot ship goods anymore. But I think that serves as a good example because it shows it is done already in the Great Lakes. So that could be used also as a model, kind of on a smaller scale, for the Erie Canal. So this in the Great Lakes shipping is mainly done to the iron ore, right? So it basically moves the iron ore basically to the big converting plants in Chicago and in Erie, and also at the areas here. So the ships go all the way there. Yeah, and there's a lot of this ore is basically shipped. So and those ships are pretty big, as you can see. So this is actually one of those ships. So those ships are basically they're very long. They're 600 feet long. They're monster ships. Yeah, specially designed for the Great Lakes. Yeah, so they also can handle some ice, as you can see. Yeah, so they're able to ship through ice and sometimes break the ice. And like if you use, there's not much space in the locks if those big ships go through. And this is actually the last ship went through in 2017 when they closed the season. So, and that's a picture from Edwin H. Scott. So at the U.S. Army Corps of Engineering website. Yeah. So those ships are pretty big. And the Corps of Engineers actually, they have actually this out in as a fuel efficiency environmental impact Great Lakes navigation study. So that's actually a study that can be downloaded. And the data basically on this study was developed by the Environmental Social Impact of Marine Transportation, Great Lakes, St. Lawrence Seaway Region Research and Traffic Corporation in 2013. So, but I think it needs to be adapted for the Erie Canal. But in general, what does it tell us? So, if you use a truck and you want to transport a ton, what can you transport? How long can you transport a ton with a gallon of fuel? So, if you use a truck, basically, you can only transport it 91 miles. If you use a rail, it's 553, and if you use a ship, 631 miles. Yeah. So, but also we have to look at the CO2 emissions. Like with the truck, of course, it's much more, rail, and then the ship. Yeah. So, and I come to this a little bit later. So, if you convert that now into capacity, like if you have a 1,000-foot laker, yeah, that can carry 70,000 tons. So to do this, you would need 700 train car trains with a 10,000 ton capacity. Yeah, 100 train car has basically 10,000 ton capacity. One train car handles about 100 ton. Yeah. You would about need 3,000 large trucks with 25 tons each to handle basically just what one ship is doing. So it makes economic sense to do this, and this is data by the Army Corps of Engineers. So I think it's not kind of made up data. So the New York State Canal System, or the Erie Canal System. So the Erie Canal, we know all, goes basically from the Hudson River all the way. It can go all the way from here, all the way in one of the Great Lakes. And this is kind of a little bit easier map to read, so it makes it a little bit more clear. So we can ship, we could theoretically ship, we could ship material all the way from here up, all the way to the canal system, all the way to Lake Erie, and then from Lake Erie can be unloaded and transported anyway to the Great Lakes to any other region, or vice versa, could be used there too. So goods that basically delivered here could be uploaded and may go in here, or we can go in Lake Ontario through the Oswego Canal System, because that's already in place. Yeah. You can also go with the attachments to the canal. They can go in the various finger lakes. Yeah. So the system is already in place. It might be a small system, but it makes sense to ship with a smaller barge goods. Yeah. And there were barges designed. There are not many or almost none operating. Lately, we saw in the news that they ship basically large vessels with barges, because it's cheaper with shipping in the river than shipping on the highway. And this is actually a picture I found. This is actually this ship was actually built in 1921, and it's almost 260-foot long barge that was specially designed to move on the Erie Canal. Yeah, and in this ship you can handle about 1,600 tons. So that's the maximum carrying capacity you could build a barge for the Erie Canal. So if it would be designed like this. The ship is retired. This is a museum now. So the design plans are there. So it could be all refitted with new stuff like electromotors, or to make it totally sustainable. Yeah. So coming back to this picture, what would it take now if we take this data and convert it to the Erie Canal system? So we know this. We have the 1,000-foot lager, and now we have a 300-foot canal barge, which can carry 1,600 tons. So that would be 16 train cars with 100-ton capacity in one barge, right? Or 64 trucks that be taken off the road. So it's a much smaller scale, but it would make sense for some of the products. Probably not for all, so everything needs to be evaluated, but it would make sense to do that. I had to throw that in because hydropower is also important, since we have the New York the Erie Canal system, and we have all those locks. And by looking at all those locks and driving by, sometimes you see, oh, there's a lot of water running over, right? So we see water running over the dams. Sometimes it needs to run over because a hydropower plant needs a certain height to operate the most efficient, so you have to run at some point water over. But this water is lost electricity. So, and years ago I was thinking with my students, what could we do with that? So
just move back.
Sure.
On the left-hand side, so that's a hydro plant.
That's a hydropower plant here. Yeah, you can see basically. Good catch, Ed. Thank you. This is a hydropower plant basically here, and you can see the water running out here.
Is that in Fulton?
I don't know where this picture comes from. It was not on the I found it on the web, but it is from U.S. Army Corps of Engineers. So there could be. I don't know. Sorry. But the main purpose is it shows there's some water lost, right? Because the hydropower plant needs a certain water level, and sometimes you have to discharge it over, because if it's too much, then you lose performance. So you have to regulate with the locks basically, also the hydropower performance. So I was thinking, well, we can use some Vortex power. Vortex power is kind of something like if you look in your bathtub and you pull the plug, then you generate at some point this vortex. But if you have a large enough vortex, you can run a turbine. And basically it would look something like this. So you have a large vortex, generate a vortex, and you have a propeller in there, and that drives a small electromotor. And you discharge the water down here. So, and you only need about 3 feet of height, so you don't need a dam actually. You can divert the water and run it through the hydropower plant, and then the water is discharged. And it won't harm the fish because it's not going fast. It's not taking out oxygen, it actually introduces oxygen into the water, whereas hydropower plants take oxygen out and then the fish die because there's no oxygen in the water, because everything accumulates in the middle. And then the fish have nothing to breathe. The fish might not die going through the hydropower plant, yeah, to the turbine, but it dies because there's no oxygen. And then this is kind of some preliminary study my students did on this, and we could basically, based on the head and then the water flow, we can probably generate something in this area on hydropower for each. It's not much, but it's a little bit. But if you put many of them in there, and they're probably not very expensive because you don't need a dam, you can divert the water, you can substitute some of the energy. Okay. So just I had to throw that in because I think it's important that you can save energy. So
there's no Vortex plants right now?
No, there are some of the Vortex plants that are actually existent in Europe. I think 3 or 4, mainly not built by private persons because they got the water right and they installed it. They are running, so it can be done. The technology is there, and we'll try to redo it in a laboratory setting, try to scale up. And actually the numbers I showed, they are pretty, we got the numbers are pretty comparable with the numbers others have figured out. So I think it's feasible. It's just a matter of proof of concept. So you need to install a small one someplace and then see, compare the numbers again, because otherwise if you have nothing to show, then nobody wants to build something. So going back to the canal biomass study. So at the time, I think this was in 2013, we looked what could we do with the biomass. So, and we looked only for biomass for wastewater sludge. So from wastewater treatment plants using the sludge that's produced in wastewater treatment plants and producing basically bioenergy from it. So what happens? So the wastewater treatment plant produces biosolids, so they're going to be trucked and to a biogas plant. Now, what's happening right now? Well, in Syracuse, some of it is basically, there's a biogas plant there, and they make electricity out of it. Sometimes they flare it. If you drive by there, you see the flare going. And then some of the biosolids, normally the normal purpose, you take the biosolids and they go direct to a landfill. And you have to basically water the biosolids and then you bring them to a landfill. Otherwise, if you ship the water, then it's not kind of a good solution because you pay for shipping and a lot of water. So what we did basically, we looked at, well, we could use the train to ship the biosolids from the wastewater treatment plant. We could use a truck and we could use a barge. Yeah. Goes to the biogas plant, and then of course the biogas plant has something left over because the biosolids, bacteria has produced something, and then at some point they die, and not all the biosolids are used up. Yeah, because there's the efficiency problem. Because at some point it doesn't make sense to run the digester 10 more days because you're not producing enough gas anymore. So some of it will have to go to a landfill. Another part. And we didn't look at that study at that time, just looking at a landfill, but what is done in Europe, if the biosolids are basically converted in a biogas plant, there are 2 ways. So it's converted in a biogas plant and the remaining is basically burned to produce additional energy. Or they use all the biosolids and it can go, instead of the landfill, it's burned, and then you just have some ash over, which can be then put in the landfill, but the volume is much less. Yeah. So the biogas produced in a biogas plant, of course, can be upgraded in a station, and you can make CNG out of it. You can clean it, put it into the grid. This is actually done in Europe on a large scale. Yeah. Like in Denmark, they don't want to. They had an initiative to be independent from natural gas from Russia. So they have a lot of biogas plants, and they produce almost all the energy they need for their purpose. And also, certain cities in Germany are also self-sufficient. They have their own biogas plant. They produce all the electricity and the heat they need for their residents, and they don't need any outside energy. So there's one of those energy cities in the Black Forest, close to Freiburg, and one of those cities is, I think, in eastern Germany, and some of them are in northern Germany. So this is basically the scenario we look like. So, and we selected basically two locations at that point. We selected basically area close to Oswego, and we selected Amsterdam as an area. And then those circles basically represent where the biomass could come from, and we looked at what types of shipping we can do, right, for different areas. And this is basically what we carried out at that time. Yeah. So as you can see, the blue is the barge, and that's the cent per ton of mile. For Oswego, it would make more sense actually to use the truck, because it's too close by, so it doesn't make sense to ship it, because you have to load it to a ship, and then you have to bring it someplace to the biogas plant. Yeah. For Amsterdam, the rail is kind of the better. So, but it really depends. So you have to evaluate for each biomass. You have to investigate what makes actually sense. So that's a cent per ton a mile. So for Amsterdam, it would make sense to use the barge, for example. Yeah, the barge is basically here. Here's the truck, more efficient. Yeah, and it depends what you do, what biomass you have, and what concept you want to build. Yeah. And then this is basically where we can get the biomass from. So for the radius for Oswego was about 50 miles, or the Oswego only, or Syracuse city metro. Amsterdam, we had a 30 miles radius, plus New York City, so it's a big difference. And then for Amsterdam, we had a 30 miles radius, New York City plus Syracuse metro. And then, if you take, for example, biosolids, it's not just only the bioenergy what produced, you also get some tipping fees. So you would also get a tipping fees. You would compete with the landfill, but as soon as Seneca Falls closes, you're probably pretty competitive, because then stuff has to ship much farther distance and gets more expensive. So this basically was a study based on the Seneca. So we use data to ship landfill data of the Seneca Meadows. Once this is closed, then it's a total different ballgame. And then basically it shows how much a given biogas plant would take on return of investment. So what can we do with biogas? So, or where it can come from? So biogas or bioenergy can come from various sources. So we can have biomass, and then talk about later. We have all the agricultural biomass. We can also produce natural gas, and we can produce autogas. It's called in German, like this from Germany, so LPG and CNG. So basically what we do with the biomass, we can basically use a gasification process. We can ferment it. We can make CBG, so that's kind of compressed biological gas. So that's my term. We can also make CNG or LPNG, depending. And then we can run it either in an engine, produce electricity or heat. So there's a lot of different possibilities. It could be also, we are not having a biogas plant. It could be kind of a gasification plant or wood fire boiler or something like that. Really depending on the application, and it's also depending what you want to do in the end and what your goals are. So that's kind of the overall scenario. So now we want to talk a little bit about the New York State canal green industry. So, and I decided to put this in. This is basically the chip or the heat and power system we have installed at SUNY-ESF in the Gateway Center. So we have basically turbines installed that are fed with natural gas. We also have basically boilers that are running with natural gas, and we have a big pellet boiler that basically produces steam for the whole campus. So the what I want to show you this slide, we don't have to invent anything. The technology is there, so we don't have to worry about the technology. It's proven in other areas, it's proven in the US. So we just have to piece basically things together that are already existing and improve the system overall performance. Yeah. So feedstock, a lot of different feedstock, and that might be even not all. So we can use woody biomass. We have pellets from various biomass to produce pellets. We can have biomass from byproducts, agricultural residues, crop residues. So there's a lot of biomass available that not yet makes it economic to ship long distances, but maybe using the canal system would work. So we can produce also industrial byproducts, biosolids, and other byproducts. The other opportunity, so this is the firing it. The other opportunity is making basically biogas, and this is actually a 1 megawatt biogas plant that was built in Germany. So I got it from a friend basically that owned the biogas plant, and the company is still not cheap. So what kind of feedstock can you use in biogas plants? The feedstock, it's already proven in Germany. In Germany total there are almost 9,000 biogas plants using all kinds of feedstock from slaughterhouse waste, paper mill sludge, waste byproducts. So all kinds of feedstock can be used, even from grass clippings. So stuff that's basically cut the lawn, that's cut every week. Golf course clippings, everything can be basically put into biogas plants and be converted into biogas plant, into biogas. Distiller grains, acid waste from the yogurt plants, industrial type products. And density matters, of course, and that's basically like what I said before. Like if I have loose straw, yeah, grams per liter. So if you have a 1 liter glass, yeah, or if you would say a cubic meter, then we'll talk about 4 kilograms per cubic meter. So if you look at a straw, for example, loose straw is about 40 grams per liter. If you have a straw in bales, it's almost 5 times more. If you have straw pellets, you can have even from the straw bale, even tripling the transport capacity. So if you make pellets, they have a higher energy content, so you can also transport it much longer distances. So it's a matter, how do we prepare also, if you think about green energy, we also have to think about how do we convert the energy or the byproduct into a transportable product, and then to make it a chip. It doesn't make sense just to dump it on a truck or on the barge and ship it. We first have to make it denser and ship it. But those technologies are already out there. I know there's a big project going on in the Ukraine. Ukraine is basically, their main product is corn, yeah, wheat corn, and they have tremendous amounts of straw. So we're talking, it's basically like to go to Kansas, even bigger. And the straw is all plowed under. So they're thinking about using the straw and making electricity, but to transport the straw, they have the same problem because the straw is very loose. So they have developed now with, I think, Chase, they have developed basically equipment that is attached to the harvester and that produces the pellets right away. So it takes the straw and makes pellets. The pellets are not small like we know it. They are basically some size. They're much bigger, but that's basically what they are working on right now. And then those pellets are moved to a future biogas plant then, and then converted in electricity. So here again, how feedstock, the feedstock would look like. So if you have basically 1 hectare, 1 hectare is about close a little bit more than 2 acres, we get about 1.6 to 2 metric tons of straw from it, right? And then 1 ton of straw yields approximately 187 to 307 cubic meters of biogas. And if you say biogas is about a 50 to 52% biogas content or methane content. And these are basically data that are used for sizing bioplants in Germany, so that's a certified data. So depending on how much biogas you need, so you need basically 1 cubic meter of methane, it equals about 10 kilowatt hours. So thermal energy. If you convert it, then you have basically the engine has only a certain efficiency, then you get, let's say, 40% efficiency, 60% is transferred in heat, and 40% is electricity. So if you have an engine, you always lose the 60%. So, but you can recover this energy and sell the heat in someplace else, or you make steam out of it. So this technology is also used. So it's just a matter of having the right customer. So it only makes sense to build large biogas plants on one side. There's a large industry that might be able to take the heat, so you can sell the heat. If you don't have a large industry that does not use the heat, then you lose out on this part. Yeah, but you still can sell the electricity. And then electricity price, and I don't have that on there, they are very different. I don't know exactly how much electricity industry has to pay, but like a farm pays maybe 14 cents or maybe only 8 cents. It depends really where they are and what contract they have. In Germany, normally you pay about 20 cents per kilowatt hour, and the farmers that produce electricity, they get 20 to 25 cents. There's also something in there now, holding the biogas in storage and have larger engines, and then just during the peak time, the engines run for 4 hours over lunchtime, and then 4 hours in the evening, and then they get the premium. So it's actually more efficient for the farmers. So basically, farmers, in addition having their feedstock producing milk or other agricultural products, they become energy farms and make actually additional money. Yeah, and they have a lot of heat. I know a farmer, he cannot sell the heat, so all he put basically like Syracuse does, he has heating for the Waterways. He built a pool, so the pool is heated even in the winter time because the heat is there and you cannot sell it. So he's in the house and everything. So things like that. Okay, so New York State Canal, you mentioned the potential. So I was thinking about that. What could be done? So, and if you see, this is basically one, I don't know which one is it in New York, but this is one of the wastewater treatment plants in New York City. Yeah, and New York City parks, and this is one of the garbage facilities that New York City has. So all the stuff is dumped in there and basically recycled and reused, or then put into landfills. So basically what happens, you see here large bigger trucks, because a garbage truck can only handle about 10 tons. So if you want to ship it someplace else, you need to put in bigger trucks or in rail cars. So, and this is actually older data, but this is what I found on the web in a short amount of time. So in 2001, New York City, and it's probably more now, generated about 13,000 tons of garbage every day. That's a lot. And that's how the garbage is basically distributed. So 31, this year, we're not looking at, because that's a recyclable, so that can be recovered and can be used. You want to look at things like this here, like from this 13,000 tons, 31% is organics, and about 18% is food scraps. So, and the average garbage truck can handle 10 tons. So you can calculate by yourself how many trips of garbage trucks they have to do every day. So it's a lot. It costs a lot of money. So basically the food scraps refer to about 2,122 metric tons of food waste. And if you to take food waste, you can generate about 90 cubic meters of biogas. And actually, those data I took, there is a biogas plant, a plant operated by the city of Augsburg, which is a large city. They take all the biomass waste, which includes food scraps, and this 90 cubic meter is basically what they get in biogas based on a ton of garbage they use. So that would basically yield about 200 cubic meters of biogas with 560 with 55% CH4, or 201,000 cubic meters of biogas. I forgot the comma, so I'm still sometimes confused because in Germany, where you use a dot, in the US we use a comma, so vice versa. So sometimes confusing with the money when you move money and see money. No, it's not like. So that translates basically to about roughly about 46,000 kilowatt hours of electricity, or 157.6 million BTU thermal energy, or 70,000 kilowatts of electricity if you take the thermal energy and convert it into electricity. But then you still have the close to 30,000 kilowatts left over, which you can sell as heat. So, and if you take the average household kilowatt usage per month, so you could basically power with this about 13,600 households just from the food scraps, if you think about it. Yeah, so it's a lot. So coming now to the New York State Canal, what would it take, or what does it take? So here we have the biogas plant from the previous biogas plant. So we have basically here, we have the fermenters here, hydrolysis stage, and then the power units here. This here is basically storage. So this really depends, and we'll talk about this a little bit later. So this is the general biogas plant. Yeah. Fermenter hydrolysis basically takes about 1,600 square meters plus 20% working space. So it's about, for 1 megawatt conventional biogas plant, you need about a half acre. And to do that with a 20-day retention time, you need basically those fermenters, and those fermenters have each 1,000 cubic meters, which is 250,000 gallons each. So you need big tanks, big concrete tanks to do that. So, and I color coded it a little bit to make it a little bit more understandable later on. So the fermenters are green, the hydrolysis unit is kind of brownish, and the energy unit is kind of a little bit orange red. So for the space requirement, so again to the space requirement, in addition, in Germany you have to hold your effluent. If you're using manure, you have to hold it for 3 months. New regulations are 6 months. So whatever you run through your fermenter, you have to be able to prove that it can hold it for 3 months. So you have to have 3 months of storage capacity. Yeah. The new regulations are 6 months storage capacity. So everybody has to build more storage capacity. So
Why is that?
That's a governmental regulation.
What was the reason for that?
Because if you have a manure plant, you cannot spread in the winter time. So, and you have to be able to hold. So the new regulations, if I believe, is you cannot spread starting in November, and you can spread starting in March. So you have to hold now for 6 months. You have to have 6 months holding capacity, because sometimes manure stinks, right? And that's also for the farms. Biogas manure actually doesn't stink that much. Yeah, but the same thing that's for farms that have large farms that have produced manure, they cannot spread in the winter time anymore, so they need to wait till you have nice weather, so it goes right away in the ground, because people don't want to have the smell. So, and that's kind of driven through kind of government. So that's the new regulation. Everybody has to, in a certain time, basically adjust to it. Yeah. So let's say this is just 3 months storage capacity. So you need another 4 tanks with 250,000 gallons, so 1 million gallons. holding capacity. Might not apply here, yeah. So, but I wanted to show that. So, which is actually a larger area too. So you need almost the same area of land to hold the storage capacity. Okay. So there are two types of digesters. We have a conventional, and I don't want to go into much detail about digester technology. Conventional digester, big tank, you throw your stuff in, the bacteria do their work and they generate the methane. So there's now a new type digester system available also, that it's kind of fixed film reactor and it has a much smaller footprint. Yeah. So the advantage is the bacteria are growing basically on a media, and the food for the bacteria, the biomass, is basically moved through those digesters. Biogas is produced and then it can be used, but the footprint is much smaller. So, and I have basically color coded those areas. So we have a fermenter, 1200 cubic meters, and a fermenter that size has the capacity about creating about 83 kilowatts. Yeah, let's say 84. Then you need a hydrolysis unit for it, and you have the storage capacity. And we have basically receiving space, and we have utility. And this is the new technology, which a smaller footprint uses about only 400 square meters, and it has 300 kW. So this is the general biogas plant. So with the fermenters, the storage capacity, and I only used one tank, so a huge tank, so you can buy huge tanks instead of building Vortex. So just to show the space. So half of the footprint is basically the storage capacity. So if you do the new technology, so you have only 600 square meters, so which is much less space. Yeah, so the plant size will go down. The same size. If you, oops, sorry. So this is the size before was basically a biogas plant that would be fed with biomass. If you have manure, there's not that much in, so the same size of plant would only produce 250 kW. So don't force basically compared to a megawatt biogas plant. And a biogas plant would produce about 300 kW there. So how would it look for a 4 megawatt biogas plant? So as you can see, you would need a conventional plant needs a lot of fermenters, and it's a lot of space. So we are talking about almost 2 acres of space just for the fermenters, and another almost 2 acres just for the storage. That might be not applicable to the US. If you have, for example, a wastewater treatment plant there, then you would not use these because you could treat the effluent to a certain level that you can maybe discharge in the lake, or you could discharge it into a river. If you would use a hybrid fermenter, then instead of having 2 acres, you would only need a half acre to do the same stuff. Storage capacity is the same because you're moving the same amount of liquid through. So the plant size would be significantly lower. Yeah. So looking about now, if you say, well, we want to generate a monster plant and use all the food scraps, so we can carry all the food scraps from a lot of different places, and we have, we're using food scraps from Buffalo, from Rochester, from Syracuse, and we'll make it a centralized plant, and we move everything to one location. So making 17 megawatts. Yeah. So we basically, if you have a conventional plant technology, we would need about 40 acres just for the tank, to building the tanks and all that kind of stuff. Yeah. And we need another 32 acres of storage capacity, which we might not need if there's a wastewater treatment close by or could be utilized. If you use new technology, we only would use about 8 acres for the plant. Yeah, so very small. So it depends really what you're looking for, what technology can be used, what is out in the market. Yeah, so there's a lot of different technologies out of the market to make it smaller. So going conventional might be not the way to do. Maybe a combination of burning, maybe a combination of biogas. It really depends what kind of feedstock we're using, how we set up the whole thing, what space is available, what all industry sites are available on the canal system. So, and that was actually my talk. And of course, I had to put that in from Albert Einstein, since he was born in the town where I grew up almost. So, so important thing is not to stop questioning. Curiosity has its own reason for existing. So always think about new things and go ahead and plan the future and make things better for the generation. Here's my email and phone number, so if you want to call or email me, and of course, question and answer.
We do have time for questions.
Sure.
Do we do any of this in this country? Is it all just done in Europe? Because I don't ever hear about it in these countries.
Yeah, I think there are some biogas plants in Europe, but it's not to that extent. You know, if you look at the in New York or the EPA website, there are not that many digesters. I think maybe 250 digesters, maybe in the US.
I work in this field on the transportation side, and there's a number of digester plants out in the Midwest and in California now that are selling the natural gas as renewable natural gas, either to the pipeline or to transportation, and they're getting tax credits for it. And there's more credits going to renewable natural gas now than ethanol, because apparently it's less expensive to produce it. And then here in central New York, the village of Manoa is making biogas at their wastewater treatment facility. I think it's kind of a demonstration project.
Yeah, I know I'm involved in that. So. Yeah, we're producing some biogas there. So I'm involved in this project, I know that.
Oh, okay.
So I'm one of the founders initiating the project.
You're working with Steve.
Okay. Steve is a good friend of mine. So. Yeah, and Manoa also has a CNG truck where they plow, so they have basically a compression station
small compressor.
Small compressor. And if you look in Europe, in Europe you can basically buy a car that runs on GNC and hydro, all kinds of fuels. You know, any car you want or any car model is available as a hybrid, as electro now, as a CNG, as LPG. So you can get basically any kind of vehicle you want. And they have also the gas stations for those fuels there. So here we have not initiated that yet. But I know in California there's a decision. So they have looking at the big lagoons on the because they're big farms. They're farms with 30,000 head cows. So and covering the lagoons and taking the biogas from the lagoon instead of moving it into air, compressing it, and then transporting it as a fuel sub. So they are probably a little bit ahead of New York, but probably over time it will.
There's a lot more funding for it.
Yeah.
Other questions? Any questions from those listening in? Nope.
Any more questions?
Thank you, Klaus. Thank you, Andy. Thank you all for joining us. I invite you to join us for some refreshments outside with additional conversation with Klaus.
Sure.
Thank you. Thank you.